Hello, everybody. This is the video for section 6.6, Parameterized Surfaces and Surface Integrals. So we have been doing a lot of work on, integrals in general, but, line integrals to be specific. Now we get to parameterize something with higher dimensions, basically two-dimensional things that live in three-dimensional spaces. And these are surfaces in 3D, and you have seen them before. But now we get to parameterize these surfaces and take integrals on those surfaces. All right, so let's get started. This is a long section. We will probably end up having 4 parts to this video lesson, but I hope you'll learn well. All right, let's get started. Okay, so section 6.6 is on surface integrals. Basically, we will be looking at 3 different types of integrals, but they happen now on surfaces that are parameterized. So the first thing we have to talk about is just really how to do that, okay? So this video or this lesson on the section 6.6 consists of probably 4 sections or 4 parts. The first one, I will show you how to parameterize surfaces, because that's the first thing we have to do everything else. And then we'll find out how to evaluate the surface area of that surface you just parameterized. And then if there's a real valued function on that surface or every point on that surface that lives in a 3-dimensional space, then we can do the surface integrals, right? And it turns out one of the important applications of surface integrals is the flux integral. Okay, so we have seen flux before, but in the past, flux was referring to fluid or energy going across a curve. Now we talk about the fluid or energy going across a surface. Okay, and then finally we'll have additional examples. So this will be a long section. Brace for impact, get ready. All right, let's get started. The first thing we should talk about is, again, going back into Calculus 1, when we talked about, just the x-axis, all right? Everything was one-dimensional, good old days. You can only go right or left. And there, we talked about this closed interval from A to B. And if you take the integral of, basically the constant 1 function, you can put 1 here. You don't have to, but this is basically the length of the interval, right? B minus A. Or you can think of that as the area over the interval A, B with the constant function 1. Okay, that's another way to think about this. But if there is a value of the function defined, like let's say for every point x on this interval a, b, then you can integrate that function, right? And so we talked about this before. I mean, this is, you can think of this as the area under the curve, assuming that f is, non-negative, or you can think of this as the mass of this interval from A to B. Imagine a rod or a stick that is this closed interval AB, where every point x has the density defined as f of x. And so it could be referring to the mass with density f, right? Basically, it tells you how heavy this stick is that is from A to B. So it has a couple of different interpretations. And what we have done in Calculus 3 is to take all of these ideas and throw this up in the space, whether it's 2-dimensional or 3-dimensional spaces, 2-dimensional space being the plane, the XY plane. All right, so just imagine we parameterize a curve C that is on the plane with the parameterization using T, right? So we had where T is equal to A here, and this endpoint where T is equal to B. And we decided to call this, we actually defined the line integral. I said this is probably better called the surface, the curve integral, but the technical word that everybody uses, or the term everybody uses, is the line integral. Now, if you don't have anything, you can put 1 here, but you don't have to, right? If the integrand happens to be the constant 1 function, right? This is just the what? It's the length of the arc. Okay, arc length of C. How long is this curve C? That's what it answers. But if every single point has a value defined, right, and that's a real value f of x, y, then we can actually integrate that function f along C, and this is going to give you what, right? So imagine, if this is a curve like this, and then the value of the function is defined as the z value, the height, okay? So you basically have this curtain or fabric or something like that standing on top of every point x, y on this curve C, right? So in that case, you can talk about the line integral. It's a line integral of the function f as the area of this curtain. And I say it's curtain because curtains can be curved like this one, and basically that like this. Or the other analogy I used, which is I think very helpful, is to imagine a bunch of Lego pieces, stacked up on top of every point x, y on this curve C, and this integral is basically adding up all those numbers of Lego pieces, and so it'll give you the total number of Lego pieces on top of this curve C, right? Or if f of x, y happens to be the mass at every single point x, y on this curve, we can think of this integral as the mass of this curve C with the density function f of x, y, right? It basically tells you how heavy this curved stick is, a curved object is called C. All right, now we add another dimension, literally, okay, to the object of study. We have been talking about curves. Curves are these, like this curve C is a one-dimensional object. You can either go forward or backwards, right? If you are on C. Even though this curve lives on the plane or live in three-dimensional space. So when you are to parameterize a curve, right, we just need one parameter t. Okay, I mean, we need one parameter and we often call it t. All right, so we can talk about r of t is equal to, and you can have 2 or 3 dimensions. If you have 3 dimensions like this, then the first one is x, second one is y, last one is z, right? And so here is an example. What is a good example? What's a non-trivial good example of a three-dimensional or a curve that lives in three-dimensional space? Well, like cosine t, sine t, and t. You remember that? That's going to be this spiral that goes up like this, right? We call that a helix. So here's something new, right? If you are to parameterize a surface, you not only need one parameter, you need 2 parameters, okay? And these are often called not S and T, but U and V, okay? So the equation, the expression for the parameterization will be like this: R of UV is equal to, and it will have 3 dimensions because these surfaces live in 3-dimensional spaces. All right, so the first thing I'm going to do is with this as a background knowledge, I am going to give you several examples of these parameterized surfaces, okay? And I'll go from the easy to the more difficult ones. All right, let's go with the first one. R of UV is equal to 3 cosine U, 3 sine U, V. Okay, and let's say U goes from 0 to 2 pi, and V goes from 0 to 2. All right, so I want you to stare at this for a little bit. If you want to stare longer, you can pause this video and stare at this these 3 coordinates for a while, and then try to think of how you would visualize this. The key is to look at the relationship between the x coordinate and the y coordinate and the z coordinate. And you probably notice at the beginning, you know what, V does not belong to X or Y. So V goes from 0 to 2, but that simply controls the last component, which is Z, right? U appears in X and Y, and since you have cosine of U and sine of U, it's probably best to analyze X and Y in terms of, squaring and adding them. Why? Well, because the mother of all trig identities, right? That's the one that says cosine square plus sine square is 1. And believe me, that's not going to change 100 years from now, okay? The cosine square plus sine square will forever ever be equal to 1. Okay, and you can tell that to your grandchildren eventually, because it'll still be true when your grandchildren are taking AP calculus or something. All right, so let's look at this. X squared plus y squared, that's going to be 9 cosine square u plus 9, my plus is disappeared, 9 sine square u. All right, and that is equal to 9, right? So this tells you right away that you have a circle involved in this, okay, of radius 3. Okay, now z happens to be just v independently. Okay, so z has nothing to do with x and y, right? So that tells you that this is a what? It's a vertical cylinder. Okay, and you can even draw a picture of this. Let's draw a picture of this object with these as the domains for u and v. Okay, and the magical part of a Zoom lecture is that these pictures suddenly appear, just like this one. Okay, so what's going on here? Well, I think you can tell you have this circle, x squared plus y squared is equal to 9. And so that's a radius 3 circle that you see here. And z, as v goes from 0 to 2, you can go up and down on this cylinder to create this cylinder of height 2, right? And that's exactly the surface that we are going to get by this parameterization of u and v. All right. Now, another thing I really want you to consider whenever you do parameterization is as follows. So you have u and v, right? So where do u and v belong? Now, this is not something that many calculus teachers talk about, and many books don't even discuss this very often. But I think it's very important, okay, especially as you go into more advanced calculus classes. And so let me show you what I'm talking about. Okay, I have to emphasize here, over here, u and v are given in terms of closed intervals, right? U goes from 0 to 2 pi. That's from like 0 to what, 6.28 or something. V goes from 0 to 2, right? So in a sense, basically what we have is this. We have a rectangular region like this, where u goes from 0 to 2 pi, v goes from 0 to 2, right? And this rectangle is now transformed into this vertical cylinder, okay? So how does it work, right? And so it is sometimes helpful, and it's especially good when you're learning how to parameterize surfaces, to trace the image of these paths on the UV plane. All right, so this is the UV plane into the X, Y, Z space and see what happens here. All right, let me show you what I mean by this. When when U and V are both 0, that's at the origin. Okay, where is the corresponding point on this cylinder? Well, you can think of U and V both equal to 0. So you have 3 cosine 0, 3 sine 0, and 0. That would be 3, 0, 0. That's this point. All right. And let's start to walk in this direction, maybe halfway to 2 pi. So this is walking from 0 to pi. Where are you walking on the cylinder? Well, you remember V is equal to 0. So Z is equal to 0. So you're not leaving the XY plane, and basically you are walking this way. Okay, so try to follow along what's happening in this transformation, because this will make a lot more sense, and it'll help you really understand what's happening as we go into surface integrals. All right, and I'm going to use a different color here. Let's use orange. Yeah, let's take this orange color here. All right, now what happens if you go vertically here, where U is still 0? Okay. U is equal to 0 means that the angle is not changing. And by the way, by this time, you probably figured out this U is acting sort of like theta, right? U goes from 0 to 2 pi. That's from 0 to 2 pi as like theta in the polar or cylindrical coordinate system. Now, if you go vertically along this orange line, you're basically going right here, okay, straight up like this, okay? And so this whole area, which we are going to call D, okay? Now D, for our consistent notation, we're going to refer to D as the domain on the UV plane. So this rectangular domain in the UV plane is transformed by this parameterization to this vertical cylinder, which we call surface S. Okay, so whenever in this chapter or in this section, whenever I talk about S, that is a surface that lives in 3D space. D, on the other hand, is the region or the domain on the UV plane that would create that surface S by the parameterization. All right, so keep this in mind. Let's go to the second example. You ready for this? The second example is this one. R of UV is equal to U cosine V, U sine V, and U. Okay, now it looks very similar, right? So what's the difference? Try to figure out how X and Y are related. You may want to pause this video for just a second and see how X, Y, and Z are related to each other, just like the first one. Okay, X, Y, Z, right? So you can see X squared plus Y squared probably should be added. And so let's note that. That's U squared cosine square V plus U squared sine square V. And of course, this is just U squared. But then you notice this time Z is not independent. Oh, yeah, by the way, let's go ahead and write U goes from 0 to 1. And V goes from 0 to 2 pi. Okay, so V is still acting like, because you have cosine V and sine V, V is still acting like theta. Right? And maybe I should have said the same thing here. This is like U is like theta. Right? Okay, so what's going on with U? Well, what's wrong with U? All right, no, U is, well, if U is squared, it's exactly what Z is, right? So this is actually Z squared. Now you have a good idea of what it's supposed to be. X squared plus Y squared is equal to Z squared. Oh, and by the way, U, which is Z, and that is between 0 and 1, right? So Z has to be only between 0 and 1. So this will give you a double cone, but this is only the top part of it, okay? So the picture is going to look like this. There you go. Okay, so the bottom, the vertex is the origin, of course, right? And then you go up to the point where Z is equal to 1. There's nothing here. Even though if you graph this one, and you have plus and minus everywhere, so you're going to have the top and the bottom. It's a double cone, but because of this restriction that U is between 0 and 1, you just get this small thing that looks like your coffee dripper, right? Or coffee filter. And so that's what you get. Now, this is the surface parameterized by this parameterization R of UV. All right, so take a look. Let's do the same thing. What is the domain D, and how is it related to the surface S? So I'm going to draw a picture as before. All right, so this is the UV plane. And this time, U only goes from 0 to 1. V goes from 0 to 2 pi, which is, over 6, right? So this is like a bigger than a 6 by 1 rectangular region. And this is the region we call D. Now, I'm going to use this letter D in integrals. So that's why I'm trying to emphasize this, all right? So every time you see D, think of that region in the UV plane. And this rectangular region is magically transformed by this parameterization. I use T to represent this transformation magically to this coffee dripper or the cone, right? How does it work? Let's follow this, right? So I'm going to pick this point here, 0, 0. Okay, so that would be 0, 0, 0 because every point has U and the U is equal to 0. So that's this point here. That's the origin. Okay, now V, what's V? Let's follow right here this way. What's going to happen as you go from 0 to 2 pi, where U is constantly 0? Notice here along this blue path or blue curve or line, whatever, as you go from 0, 0 to 0, 2 pi, 0 comma 2 pi, u stays 0. So z stays 0. So where are you moving as you, if you're standing right here, right? The answer is actually you're not moving at all, okay? So this is the place where, you're staying at this vertex as you take this, right? So all blue points are here. Now, if you have to move, then you could imagine yourself just turning around, like, just turning around one time at this point as you stand there. That's the motion as this UV goes from 0, 0 to 0 comma 2 pi. All right, the orange color, you go in perpendicular direction. What happens then? Well, here the angle, which is represented by v. By the way, I should have not made this v as in vector. This is just simply v, okay? Not a vector. And I should have written this in black ink. All right, so that's what's happening here. Now, the orange one will take you as u goes from 0 to 1, but v stays 0. And if this is 0, okay, you basically have 1 here and 0 here, right? So it'll be following u, 0, u. And so that would be a line like this, where this point projects down to the x axis, and this will be a 0.100. Okay, so that's what's happening here. And again, this point is not emphasized, like what happens to these pre-images and what happens to these paths as you go from the UV plane to the XYZ space, but it is something to keep in mind, and this will help you visualize what's happening. Sometimes you have to follow a certain path on the UV plane to see what's happening on the surface S. So this is S, the pre-image is D. Okay, example 3. This is actually a pretty important one. Okay, I know, the other ones are important too. We have so far done cylinder and a cone, right, a circular cone. All right, so this one will be UV, R of UV is equal to sine U cosine V, sine U, sine V, cosine U. Okay, this time let U be from 0 to pi, and V to go from 0 to 2 pi. Okay, so what do? Well, you always, try to find a relationship between x, y, and z. So let's do this. Let's do x squared plus y squared. And then you get sine square u, cosine square u, plus sine square u, sine square v. That's the first two terms squared and added together. Notice here I can factor out sine squared of u. And the rest is cosine squared. Oh, I misspelled. I made a typo, even though I didn't type anything. All right, so, okay, so you probably noticed this is cosine v. So if you square that, this should be cosine squared of v. Okay, and I will just write in red because first time I made a mistake and I don't want you to keep writing the mistake. All right, so if you factor out sine squared u, you end up with cosine square v plus sine square v, which you know as simply 1. Okay, so this is sine squared u. Now, it's not exactly z, right? Oh, but look, then x squared plus y squared. And then if you add z squared, watch what happens. Wow, looks like what? Sine square u plus cosine square u, because that's your z square, that is equal to 1. Right? What does that look like? I hope it looks round to you. X squared plus y squared plus z squared is equal to 1. This is otherwise known as the unit sphere. Okay, and that's exactly what's happening here. Let me draw a picture of this unit sphere, which will look like the Earth with the north and the south poles. All right, so you have the UV plane. This is the domain D. Remember to be consistent. The UV plane, the domain is called D, and the parameterized surface is called S, which is the unit sphere of radius 1. So like this point is, 1, 0, 0, right? And then the highest point, of course, is 0, 0, 1, and the south pole is 0, 0, negative 1, and so on. All right. Let's try to figure out what happens when you're at the origin, 0, 0, 0. Okay, so you have 0, 0, and then cosine of 0 is 1. So we are at 0, 0, 1. Where is that? Okay, it is at the North Pole. Okay, so this represents the blue, the image of the blue dot I have here. Um, okay, when both u and v are 0, you are standing at the North Pole. Now let's move which direction? Let's go this way. All right, so I forgot to mention here. So u goes from 0 to pi, and v goes from 0 to 2 pi, right? And you can probably guess this is actually acting like what? In spherical coordinates. And by the way, this is x, this is y, this is z. This is very much like spherical coordinate conversion. So u is actually acting like phi, and v is acting like theta. It's all Greek to you. Yes, I know. All right, so that's what we have. Right? And so if you start to walk in the blue direction from 0 to pi, guess what? So v is staying at at 0, and the u is moving. So what happens is, as cosine goes from cosine of 0, you're going from cosine of 0 to cosine of pi, which is, well, here's cosine of pi over 2, and cosine of pi over 2 is 0. And so you're actually following along here. Okay, now the reason I know I'm going in this direction right to the point 1, 0, 0 is because right here at this point, maybe I should pick another color for that. Right here at that gray point, okay, right here at this gray point, what is that? The u is pi over 2 and v is 0, right? And so if you look at this, this will be 1, and then 1 times let's see, 1 okay, so at this point v is equal to 0, so this will be 0, right? So it's going to be 1, 0, 0, and so it's this point that you are at. And if you keep walking, in along this blue line here, you will be going this way. All right, so that's what's happening here. Now if you are just keep walking this direction here, what happens? Well, as long as u is 0, the cosine of u is 1, so you are right at this point, just walking, actually not even walking, you're just turning around at the North Pole as you go in the orange direction. So let's use another path here. How about bright blue one like this, okay? If you're standing at this point, which is pi over 2 comma 0, that's this gray point. And if you start walking in the green direction, then pi over 2, the u of pi over 2 stays the same. So cosine of pi over 2 is 0. The z value stays 0. And then you are going around this way. Okay, so that's what's happening on the surface of the sphere. So the relationship between the domain D and the parameterized surface S can be considered this way. All right, I'm going to give you a couple more examples. Stay tuned. Example 4. I'm not going to do all the details here. Oh, by the way, here is a more general statement. When z is equal to f of xy, then you can use this standard way of parameterizing this, right? Because if z depends on x and y, and if z is a function of x and y, what that means is that for every x and y, you have a unique one and only one value z, right, which depends on x and y. So in that case, you can use the standard parameterization, let x be y, no, let x be u, y be v, and z will be f of u v. Okay, so that's very standard. So that's a case where you have, like something like this. For each xy, you have f of xy as your z value. And so whenever this is true, then you can always do this. Okay. So for instance, here's an example within example 4. Um, if you have z is equal to x squared plus y squared. Now, what is that? Okay. Yeah, that's a parabola. No, sorry, it's a paraboloid. It's a circular paraboloid. Okay. We have seen this many times, right? This is the origin, and it just goes in here every, well, you in traces, you have a parabola, another parabola, and then you have a circle if z is positive. Okay, so you can parameterize this simply this way. R of uv is equal to uv and then u squared plus v squared. Okay, that's perfectly acceptable. But this is rectangular, right? So if you have to integrate this, if u and v are rectangular, then you would be integrating this over a rectangular or rectangle or a square or something. Right? If you want to sort of take a circular approach or polar approach, you could also parameterize the same paraboloid in a more polar friendly or cylindrical friendly way, which is this. Watch. We can also parameterize this as u cosine v, u sine v. Now, this is something you have to learn. I haven't asked you to parameterize anything yet, right? Except for the simple case. And so what allows us to figure out what the parameterization should be? Okay, so the idea is here, you see a bunch of circles, for, the every um, level curve is a circle, right? That is parallel to the xy plane. So you want x and y, x squared and y squared to be having cosine square plus sine square. So if you do this, okay, then you see x squared plus y squared, and I think you can see this now. It's going to be u squared, right? And you want that to be z. So then you just go ahead and insert u squared here. Now this is very similar to what you saw earlier for the cone, except in cone, you only had u as your z. But if you let z be u square, okay, then you have this equation, z is x squared plus y squared, and that is a parameterization of the same surface S, okay, but this is rectangular. And if you have to pick a circular area, like if you have to find the surface integral of the surface S over a circular region, okay, then you probably do not want to use the rectangular friendly version of your parameterization. You probably want to use a polar friendly version of the parameterized surface. Okay, so that's what's important here. And yeah, I'm going to go into the next part of this video, which has to do with defining the surface integral. All right, so let's pause here for a moment, and then you can go into the next section, which will be referring to or talking about the surface area and more generally surface integrals. All right, so we will see you there.